High above the Nevada desert, nestled near Lake Tahoe among pinyon pines and juniper trees, lies my small slice of America. Perched at 7,000 feet above sea level, this is true snow country. For nearly half the year, the property is blanketed in anywhere from 3 to 8 feet of snow. If you've ever lived in these conditions, you understand how essential it is to clear snow regularly, often after every storm. That reality makes installing and maintaining a solar system especially challenging, particularly on a mountainside with limited flat terrain. In this video, I'll show you how I managed to install 6,330 watts of solar using 17 solar panels across 4 separate arrays. 2 of them are permanent installations. The other 2 are mobile and can be packed up and stored away during the harsh winter months. So let's head down and take a closer look at how I made it all work. First, let's take a closer look at my window to the sky and the solar potential available throughout the year. From March through September, conditions look promising. During this period, the sun's tilt ranges between 15 and 30 degrees, ideal for efficient solar energy capture. As we move into the colder months, the sun tracks lower across the southern sky, reaching tilt angles between 35 and 40 degrees. At these angles, solar production tends to decline due to the reduced exposure. However, colder temperatures may offer a compensating factor, potentially boosting panel efficiency. Whether that plays out in practice remains to be seen. With that in mind, I positioned the ground-mounted array as far to the north as possible to maximize sky visibility and solar access year-round. By May, with the sun climbing back to around 20 degrees and the snow beginning to melt, I should be able to redeploy the mobile arrays and integrate them back into the system. Now let's move on to the ground mount, and I'll walk you through what I've set up. We begin at the front of the permanent ground-mounted solar array. Watch as I move the panels through their full range of motion, from a steep 38 degrees down to a completely flat 0 degrees, allowing us to get a clear look underneath the array. This movement is fully controllable via smartphone, tablet, computer, or even automated systems, giving flexible, real-time angle adjustments as needed. Now that the panels are flat, you can clearly see the pedestal supporting the entire structure. At the core are 7 ground-treated 4x6 posts, each 36 inches deep, anchoring the main array firmly in place. Surrounding the perimeter, 12 additional 4x6 posts connect the inner and outer 2x6 frames, creating a single unified structure. A full breakdown of the construction process, including step-by-step images, will be presented in a slideshow at the end of this video. Moving to the side, you'll notice 4 position feedback linear actuators. These handle the raising and lowering of the solar arrays. The system is precisely balanced, with a 20-pound uplift on the front edge, and helped by 2 40-pound gas struts. This combination ensures smooth, stable motion during adjustments. At the heart of the system lies the master control unit, housed in the center of the pedestal. Let's move around to the front so we can take a look at the back of the control system. On the rear side, you'll see the PV wires enclosed in conduit, traveling underground toward a connection station and eventually to the inverters. Just to the right are the underground 110-volt input lines, followed by the 4 actuator control inputs. Above that, there's the line connected to the digital angle gauge. Now we'll move around to the rear of the structure to examine the modified EG4 mounting system and take a closer look at the front side of the control unit. As we make our way around to the back of the system, I want to point out a critical safety feature: the 8-foot grounding rod securely attached to the frame of the solar ground mount. This is a code requirement, ensuring proper electrical grounding and overall system safety. Now, looking closely at the rear of the structure, you'll notice the rafter-style braces connecting the main pedestal to the back row of 4x6 posts. These braces, much like traditional roof rafters, are anchored using 8-inch timberlock screws and hurricane ties, providing both structural integrity and resistance to high winds or shifting loads. Now let's examine the aluminum braces from the original EG4 bright mount system. If you've worked with EG4 mounts before, you'll recognize the larger vertical support post, with a smaller diagonal brace originally intended for angle adjustment. Since my system uses linear actuators for tilt adjustment, I didn't need the original diagonal braces. Instead, I repurposed them, mounting the smaller brace directly against the upright support and securing both together using half-inch stainless steel bolts, washers, and U-clamps. This created a robust 3-bolt lower mounting bracket for added stability. To further reinforce the structure against lateral movement, I installed carbon steel legs at the base. The vertical braces and steel legs are fastened with half-inch by 5-inch lag bolts, driven through 3 inches of cross grain and 2 inches of end grain, resulting in exceptional holding power at the pedestal's foundation. You'll see more details of this setup in the construction slideshow at the end of the video. Let's move on to what I call the master control unit. This enclosure governs the motion of the actuator arms, but it also contains many standard components found in solar energy systems. Since the system is currently active, I won't be opening every compartment, but I'll walk you through the major parts. For those interested, close-up images and build details will appear in the slideshow at the end. First, one component I can show you is the Fergelli FCB1 actuator control board. This board is designed for use with actuators that have built-in precision feedback sensors, allowing it to synchronize up to 4 actuators so they move in perfect unison. This level of precision is essential in systems like mine, where coordinated tilt movement is desired. Just below that is the 12-volt, 50-amp DC switching power supply. This unit powers all 4 actuators, the manual tilt switch and the digital tilt gauge, ensuring the system operates consistently. At the top center of the unit is a feature I designed, a manual automatic panel tilt switch. Built around a Shelly 2.5 Wi-Fi controller, it includes 2 110-volt switching relays and 2 momentary push buttons. This setup allows for on-site panel adjustments even without a smartphone or internet access. In the bottom center is the IMO PV array DC isolator switch, a common component in most solar installations and a required element by code. It allows for immediate disconnection of the PV array in case of emergency or routine maintenance. To the right, you'll see the 30-amp DC circuit breakers for arrays 1 and 2, installed per the requirements of my inverters, which are MPP Solar Model LV6548. Just beyond the main control board, I've also designed a custom switching unit designed to toggle between a 5-panel and 4-panel array configuration. Let me explain why that matters. According to the manufacturer's specs, each 375-watt solar panel has a standard test condition open circuit voltage, or VOC, of 47.6 volts. In a 5-panel series, that totals 238 volts. The maximum VOC permitted by my inverter is 250 volts. However, here's the issue. During colder months, when temperatures often drop below 30 degrees Fahrenheit, VOC can spike well above the rated value, potentially exceeding 250 volts and damaging the inverter. By switching to a 4-panel array in winter, the VOC drops to around 190 volts, well below the inverter's upper limit even in sub-freezing conditions. This safeguard ensures the system remains protected year-round. Now, let's continue forward and take a quick look at the PV connection station. A couple of years ago, while I was installing the new well and preparing to bring the solar system online, with inverters, batteries, and panels freshly delivered, I had already chosen this location for what would become the solar field. Knowing that, I ran 4 pairs of 10-gauge photovoltaic wire in conduit from this site directly to the inverter system located in the garage. Later, when I installed the solar arrays, I also enclosed 4 additional wire pairs in conduit leading from the array structure itself to this central PV connection station. On the left-hand side, you'll find the input terminals for arrays 1 and 2. The right-hand side is designated for arrays 3 and 4. To maintain clean, isolated wiring paths, I used Dinkel DK6N DIN rail terminal blocks, which provide solid, reliable connections while keeping each array circuit separate and organized. For additional protection, I installed 2 1000-volt DC solar PV lightning arresters, safeguarding the system from voltage spikes due to nearby lightning strikes or electrical surges. While I do have a more detailed video covering the inverter installation process, I think now is a good time to take a quick trip into the garage and bring this full circle by looking at the heart of the power system. Now, let's move into the garage to look at the core of the system. Here you can see the heart of the installation. 2 LV6548 inverters connected in split-phase configuration, delivering 220 volts to the home. To the left of the inverters is the input subpanel, which handles the grid connection. And just below that, the output subpanel, which routes power from the inverters to the main house panel. On the far right are two IMO disconnect switches mounted at the inverters. These provide a quick and accessible way to isolate the solar arrays if they need to be shut down. Over on the left wall is the EG4 chargeverter charging station, which serves two important functions. Function 1. With the switch on the right turned on, the chargeverter operates as intended, but with a useful adaptation for emergency situations. In the event of a grid outage, especially in the evening when the solar arrays are no longer producing, my home must rely solely on battery power. At that point, the critical question becomes, what is the state of charge of the batteries? If the SOC is below 20%, I might only have a few hours of runtime remaining. This is where the generator and chargeverter come into play. My generator is brand new, but it is not a pure sine wave model, meaning its output is too dirty to power certain sensitive electronics in the house directly. According to Signature Solar, however, the chargeverter can accept that generator power to charge the batteries and supply clean power to the home's sensitive loads, provided I do not exceed its rated output of 5,120 watts. Here's how I configure it. My generator has two 220-volt output connectors. One connects to the chargeverter, and the other connects to my transfer switch. At the transfer switch, I activate only those circuits that do not require pure sine wave power. The sensitive loads remain powered by the inverters and batteries. Typically, the sensitive breakers draw around 1,200 watts, leaving roughly 3,920 watts available for battery charging. By setting the chargeverter to charge at 57 volts DC and 50 amps, I draw about 2,850 watts, leaving a comfortable buffer of approximately 1,070 watts for fluctuations in load. Function 2. Switching off the right side control and turning on the left side control allows the chargeverter to operate as a standalone charger using 220-volt input from the grid. In this mode, I can isolate individual batteries for top balancing or provide a steady current for state of charge calibration on my JK BMS as recommended by Andy. In either case, the battery being serviced must be completely disconnected from the system before these procedures. Now let's take a look at the battery bank itself. Recently, I built two Yishang 280 amp-hour batteries. These units are straightforward to assemble if you follow instructions carefully. I'd compare the process to assembling a piece of furniture, like my office chair, with one key difference. A battery build demands much more precision, as any error could result in a short circuit or fire hazard. Below the inverters are the 5 batteries I've been using for the past 4 years. The two on the outside are my original units, 105 amp-hour big battery Huskies. These do not provide user access to the internal BMS, so I monitor them solely through voltage readings. In the center are my legacy EG4 Life Power 100 amp-hour batteries, which have performed reliably over the years. At the moment, these 5 batteries are not active in the system as I finalize the setup of the new Yishang batteries. Once everything is integrated, the system will have a combined storage capacity of 51,360 watt-hours at 100% state of charge. Now, let's move on to the computer interface for the solar system. I want to give you a look at how the system appears from my computer. Every control and monitoring function I'm about to show can also be accessed from my phone or tablet, making the system fully manageable whether I'm at home or away. In this first example, you can see how I control the tilt angle of the ground-mounted arrays directly through Home Assistant. In the upper left of the screen, the current angle of the arrays is displayed in real time. For precise adjustments, I can move the panels up or down in single-degree increments. Because this control is integrated into Home Assistant, I can also create automation routines to adjust panel movement based on environmental conditions. For instance, if wind speeds from the north or south exceed 40 miles per hour, the system will automatically move the panels to a 0-degree angle, allowing wind to pass freely over and beneath the array. Once wind speeds drop back below 15 miles per hour, the system returns the panels to their original operating position. This automated function is adapted from the eco-worthy tracking panel systems. Pan, tilt, and zoom cameras provide a wide range of viewing angles on the solar arrays. These cameras make it easy to check for any obstructions or mechanical issues with the panels. Having multiple perspectives ensures I can quickly identify and address potential problems before they affect performance. In this view, I'm monitoring both Solar Assistant and my JK-BMS simultaneously. Solar Assistant provides a comprehensive overview of the system, displaying inverter load and output, photovoltaic voltage and current, battery status, and grid interaction. The charting tools are especially useful for making informed decisions about how best to manage the balance between grid power, battery reserves, and solar production. Many inverter settings and automation rules can also be modified directly within Solar Assistant. As for my Yishang batteries, they are located far enough from my computer that Bluetooth connectivity is not possible. The PC application allows full control of both JK-BMS units over a wired connection, letting me view live statistics and make real-time adjustments to settings whenever necessary. Finally, I use the Emporia Power Monitor to track energy consumption at the household level. This system monitors every circuit in my home's sub-panel. If I notice an unusual increase in load within Solar Assistant, I can quickly cross-reference the Emporia interface to see exactly which circuit is responsible. While the Emporia Monitor is primarily an information tool, it allows me to track down unexpected loads and take corrective action as needed, keeping the system running efficiently. The site you're seeing here was originally selected as the location for a greenhouse. With year-round exposure to sunlight, it made perfect sense at the time. But with temperatures routinely dipping below 30 degrees Fahrenheit for half the year, building and maintaining a greenhouse just didn't feel practical. A solar array, on the other hand, made much more sense for this environment. That said, I may still build a smaller greenhouse elsewhere on the property in the future. The process began with clearing and leveling the ground, then marking the locations for post holes and wiring trenches. At the center of the pedestal, 7 primary 4x6 support posts were installed. Each hole was dug to a depth of 36 inches and filled with a 12-inch by 36-inch sono tube. Each tube was reinforced with 280 pounds of concrete both inside and around the form. The PV wire trenches were dug 24 inches deep and lined with PVC conduit to house the buried cabling. Around the perimeter, 8 additional post holes were dug to 24 inches deep and fitted with 10-inch by 18-inch sono tubes, each filled with approximately 140 pounds of concrete. These posts support the outer and inner structural frames, as well as the rafter-style bracing at the back of the pedestal. Weed-blocking fabric was laid inside the structure before the crossbeams went in, and roughly 4 tons of gravel were added to complete the foundation. As a lifelong woodworker, I have to emphasize the importance of using quality materials, and for me, that includes original Gorilla Glue. When applied correctly, it's one of the strongest wood adhesives available today. I used it throughout the pedestal build, including to bond a 2x10 across the top of the structure, as well as horizontal 2x10s on the front and back faces of the upright posts. Every contact surface was glued, clamped, and screwed, ensuring maximum strength and structural integrity. To further reinforce the mount, I added a second pressure-treated 2x10 to the top of the pedestal, again using Gorilla Glue and screws. This gave the EG4 base mounts additional cross-grain material to fasten into, greatly improving hold and resistance to torque. Each of the 1/2 inch by 5 inch lag bolts used to secure the main support braces passes through 3 inches of cross-grain and 2 inches of end grain, creating an exceptionally strong and stable foundation. What you're seeing here is the expanded version of the stock EG4 bright mount system. After mounting 12 10-foot superstruts to the EG4 base, I paused to test the balance point and verify that the added support would hold steady before proceeding. Once that was confirmed, I modified the vertical support arms as described earlier in the video and installed the linear actuators for precise tilt adjustment. Fortunately, all utilities, power, networking, water, and drainage, had already been installed during the original greenhouse project. Tapping into the existing lines was straightforward, and I was able to make all the necessary wiring connections at the PV connection station. Finally, Here are a few shots of the master control station, which I built in my workshop. The first image shows the internal layout of the control box during assembly. Next, you'll see the enclosure with some components exposed during testing. And lastly, the fully assembled and weather-sealed control unit ready to be installed out at the solar site. If you've made it this far into the video, I want to sincerely thank you for watching. A question I often hear is, you must have invested a lot in a system like this. How could you possibly see a return on that investment? My answer might surprise you. Knowing that I'm not dependent on the power company gives me tremendous peace of mind, just as much as drawing my own clean, bottled water quality supply from my well, or raising chickens for fresh eggs. But the main reason is more personal. At 70 years old, the physical effort required to build a project like this, lifting 70-pound bags of concrete and mixing them by hand, cutting and setting heavy timbers, and working day after day in every kind of weather, keeps me fit and strong. Beyond the physical work, the mental challenge of learning solar technology, understanding each component, designing mechanical systems, and programming automation in Home Assistant keeps my mind engaged and learning. I look forward to each day with new challenges and projects ahead. These kinds of benefits don't have a price tag. When the alternative is sitting on the couch, watching television, and growing old, I'd much rather be outside, working hard, using my body, and keeping my mind active. I should add that I'm not an expert in all things solar. Far from it. I learn something new every day. Nothing I've shown or described here should be taken as the way to build a solar system. Only my way, based on what I've learned. Much of that knowledge has come from people like Will Prowse at DIY Solar, Andy at Off Grid Garage, and from my brother, Dan. If you're considering your own solar project, I highly recommend watching every video that Will and Andy have produced. I'll include links to their channels in the description. Thank you again for joining me, and remember, mind, body, and spirit. If you don't use them, you'll lose them.